Okay, it's my pleasure to introduce Magdalena Larfors from Uppsala University, who will speak to us today about stringy perspectives on manifolds with G2 structure. So please, Magdalena.
Thank you. So thanks for the invitation to speak here. And the plan, as Jeff said, is to talk about manifolds with G2 structure. I'm a string theorist from the beginning, and I'm interested in string compactifications and the kind of geometries that arise in that setting. And manifolds with G2 structure appear in a number of places in string theory, or they have appeared in the past. And this is what I'll talk about. So before I go into the details of this talk, let me just say that this is what I'll tell you about is really a collection of different, explorations of different ideas that I've been carrying out together with Senja de la Osa and Matt McGill and Eric Swanes over a number of years. So since we worked on this problem or this set of problems for some time, it also means that the results that we've had have evolved a bit over time, and they have the methods that we have used have also changed a bit. So hopefully I will be able to give a coherent story of this this anyway. But if anything is unclear, just stop me and ask a question, and I'll do my best to explain. Now I'll have to check if I can get this to work. Like that. Okay, so the motivation that I have for studying this comes from string theory and the fact that in string theory there is a rich interplay between geometry and physics, where the physics is determined by the geometry, and vice versa. We can use physics to understand things about geometry. And these seven-dimensional manifolds with G2 structure, they appear in different settings in the string theory world. So first and foremost, they have been used to get four-dimensional models from compactifications of M theory. So this is very natural. M theory is an 11-dimensional theory, and if you then compactify it on a four-dimensional space, then you get something which could resemble the physics of our world. So it will have three non-compact spatial dimensions and one time dimension. And supersymmetry plays a role in determining what kind of geometry you should focus on, and I'll talk a bit about how that comes about. In M theory, it's known that if we want to find Minkowski vacuum with minimal supersymmetry, then we should choose the manifold, the seven-dimensional manifold, to have G2 holonomy so that it's Ricci flat. And this has been used in various ways to try to construct models of particle physics. Manifolds with G2 structure can also be used in M theory, and then they are being probed in order to construct solutions with different kinds of cosmology, so ADS solutions from string theory. What I'll talk about today are three-dimensional theories that arise from compactifications on G2 manifolds, and I'll focus on the heterotic string, where one can get Minkowski or ADS solutions in 3 dimensions from compactifications on manifolds with G2 structure. And supersymmetry here again constrains what kind of G2 structure we need, and I'll go through that in detail in a few slides. One can also explore these kind of geometries from the perspective of type 2 string theory, and that has been revised a bit recently because of studies of ADS solutions again, and the various interesting cases of ADS vacuum that one can find from this setting. But as I said, I'll focus on the heterotic theories. So what I'll talk about today is the supersymmetry and how that relates to the G2 geometry, so what the mathematical structure is of these geometries. Then I will talk about the deformation study and how we can say something about the infinitesimal moduli of these heterotic compactifications using supersymmetry as the main principle. But otherwise treating the problem really using the tools of differential geometry. And after having done that, I will use another tool to study more or less the same thing. So I will derive a superpotential for the three-dimensional theory that results from compactifying the 10-dimensional heterotic string on these 7-dimensional manifolds. And I will use this superpotential to revisit the moduli problem, and also, which I will say some things about an ongoing study that we are working on now since some time, which is targeting quantum aspects of this three-dimensional theory. So that's the plan for today. So just to say that I'm not talking about that there are realizations of these geometries that I'm talking about and the kind of heterotic vacua or the heterotic compactifications that I'm interested in. Here's a list of examples that have been constructed in the past. I think I have included most of the examples, but if something is missing, I just apologize for that omission. So basically, these geometries with G2 structure of the type that is required for a heterotic string, they have been constructed and in different ways using orbifolds, using nil manifolds or a similar twisted tori, and also some non-compact examples. And people have also explored since a very long time what kind of mathematical structure these compactifications have. And here is then a list of those key references. Okay, so let me set the stage for the story that I want to tell you. So I will start with the heterotic string, and I will view it in this talk as a 10-dimensional supergravity with gauge fields. And the gauge fields, they take values in E8 times E8. And so there are two versions of the heterotic string, and this is one of them. I will compactify this, and compactification, what that means is that I take my 10-dimensional manifold and I assume that it factorizes into a compact d-dimensional bit. Sorry, a compact 10 minus d-dimensional bit, which I call y, and a maximally symmetric space-time, which can have, for example, 4 dimensions or 3 dimensions that I will talk about today. And supersymmetry is a property of the heterotic string in 10 dimensions. So the heterotic supergravity has one supersymmetry. So it's a minimally supersymmetric theory in 10 dimensions. If we compactify it on a manifold, then we will get theories that if we compactify on a compact manifold, then we can get theories that either are or are not supersymmetric. And we will preserve supersymmetry if the manifold that we compactify on admits nowhere vanishing spinors. So it has to be spin. And if we want minimal supersymmetry in the lower dimensions that we're going to, so 3 dimensions in our case, then we want the internal manifold to have one nowhere vanishing spinor. And this singles out the G2 manifolds for us. So supersymmetry tells us that we need spinors in the theory, and we need those to be well defined. So we need manifolds that are spin. So then the heterotic d-dimensional effective field theory that we get, so this low dimensional theory, will be determined by the mathematical structure that consists of this spin manifold, which has a Riemannian metric. So that's the compact geometry. Then we have fields, which come from the 10-dimensional supergravity that we start with. There's a scalar field called the dilaton. There are these gauge fields. So there's a vector bundle over this manifold, and this vector bundle should have a connection with structure group in E8 times E8. Then the heterotic string has a B field, which is an interesting object. And I will not talk a lot about it, somewhat, but not a lot. What it does for us in this what it defines in this mathematical structure is that it defines a three-form flux, which is a well-defined three-form. And I will take this three-form to be defined by this equation here, which is known as the anomaly cancellation condition. So H is equal to the exterior derivative of B plus a difference between two Chern-Simons terms. There's a Chern-Simons term constructed from the connection on the gauge bundle. And then there's a Chern-Simons term constructed from a connection that I will talk more about later on the tangent bundle. And these Chern-Simons terms, they are multiplied by a constant, which is called alpha prime. And this is related to the stringy corrections of the supergravity theory. So this is the alpha prime there is something that is showing that this is string theory and that it comes from string theory. It's related to the string tension. Okay, so this is the mathematical structure. We have this tuple of objects, a manifold, a scalar, some connections, and a three-form flux. Then supersymmetry will relate these objects, and it will provide constraints on what these objects are. So just to provide some context, if we would compactify the heterotic string on a six-dimensional manifold, this kind of setting would give us the Hall-Strominger system, where we get minimal supersymmetric four-dimensional theories coming from particular six-dimensional geometries. And what I'll talk about today is then the analog in 3 dimensions of this. Okay, so let's start and talk about what the constraints are on these different objects. So starting with the geometry, this should be if we're talking now about a 7-dimensional compact geometry, in order to go down to this 3-dimensional theories that I'm interested in, then we've concluded that in order to preserve supersymmetry, we need something that is spin, and we also want something that is geometric, so that it has metric. And if you have a 7-dimensional manifold that is spin and Riemannian, then it's well known that this has a D2 structure. And this D2 structure can be defined by a three-form, which I will denote by phi. And this three-form is related to the spinner that I've mentioned, so this nowhere vanishing spinner, in the way that is written here. By the way, can you see my cursor if I do like this?
Mm-hmm. Yep.
So given the spinner, we can construct this three-form, and given the three-form, we can deduce, we can use it to say things about the spinner. I will use the differential form description of the D2 structure, because it lends itself very nicely to this deformation study that I want to do. Also, it's well known that once we have defined this positive three-form that determines the D2 structure, then this will determine for us a Riemannian metric on the manifold, and also a nowhere vanishing four-form, which is the Hodge dual of this three-form. It's not a one-to-one map between the three-form and the metric, but I will be a bit cavalier with that and basically treat them on the same level. So basically, phi will for me define the metric on the manifold. So this the spinner, the nowhere vanishing spinner, one can show that it's always covariantly constant with respect to a connection with torsion, and that can be translated to the following equations for the exterior derivative of this three-form and the four-form. So the exterior derivative of phi and psi need not be 0. And if they're not 0, then we can just decompose them with respect to the irreducible representations of the G2 group. So this is just general decomposition. Here we get 4 forms. So this is how the space of 4 forms decompose on the G2. And here we get a 5 form, and this is how the space of 5 forms decompose. So if the manifold now has G2 holonomy, then that corresponds to these 2 forms being closed. Or if we just want to talk from the perspective of the 3-form phi, then it has to be closed and co-closed. And this corresponds to the torsion vanishing, which means that the spinor has to be covariantly constant with respect to the Levi-Civita connection. Okay, so those are our G2 structures. So if we now have a heterotic G2 system, so I want now to specify the geometry that underlies these heterotic constructions with this manifold with the G2 structure. I have the vector bundles, the gauge bundle and the tangent bundle with their 2 connections, and I have the flux H plus the dilaton. Then this will give us a heterotic G2 system, and it will satisfy n equals to 1 supersymmetry. So one can write down what the constraints are on these objects in order to preserve n equals to 1 supersymmetry. And it turns out that the constraints that one has on the G2 structure is that it should be, it should satisfy this condition. So it's conformally co-closed. So here we have the 4 form, and here we have the dilaton. So this condition has to be satisfied. And once, when this is true, then there is a unique connection. So this connection that has a torsion, when that's with respect to which the spinor is covariantly constant. This now has a totally antisymmetric torsion, so I can identify the torsion of this connection with this 3-form flux H. So this only holds when we have n equals to 1 supersymmetry. And with respect to this unique connection, then all of these G2 structure defining quantities are parallel. So the 3-form and the 4-form and G are all parallel with respect to this unique connection.
But sorry, is that the unique connection you discussed on the previous slide?
Right, yes, it is. It's the same. So this always exists, but it's only unique if you have this condition, because otherwise you can write down a 1-parameter family of connections. Now, if you demand that the torsion is totally antisymmetric, then that 1-parameter family collapses to just 1 element.
But the claim is that if you do have this condition in blue, this d e to the minus 2 phi psi is 0, then that connection will be associated to this H, and it will have skew torsion then? I mean, because H is skew. But...
Yes.
Okay.
Exactly.
And does that mean one can express H purely in terms of B, psi, and G? Is it
yes.
true?
Yes. So you can express H in terms of the torsion classes, which are given by d psi and d phi. So there is
presumably it's nonlinear, I guess. It's a nonlinear combination of them, or
okay. So no, it's linear.
Oh.
It's linear, and but there are some. So I don't remember the exact expression from the top of my head. We have it in our papers.
Okay.
It is linear, but there are contractions with various things in order to get the form degree to match. Okay, so we'll have So H will have some component which is tau naught times phi, and then it will have some component which is tau 3, which is a 3 form, and then but tau 1 I think is something like tau 1 contracted with psi, and then there are numerical constants to that are determining this. But so what happens when we have this condition here is that there is one torsion class which is vanishing, this tau 2.
Okay.
And when you write down so when you write down this match, okay, let me not go too far into this because I might say something that is wrong. Okay. But it's certainly true that when this condition is satisfied, then this and you can write this down. So we can always compute what T is here, this torsion form, or this torsion quantity. And this will be skew when tau 2 is 0. And only when tau 2 is 0.
Okay.
So what I want
to say, yes. Is there any relation between theta and this unique connection nabla T?
Yes and no. Yes, there is. But it's a bit involved. So so one can relate, because you see here, so H here is related to the torsion, and here we have theta. So through this anomaly cancellation condition, we will get a connection between these things. And the way that one constructs solutions here, supersymmetric solutions to the supersymmetry equations, is by playing with this relation between theta and this unique connection. So in the Strominger-Hull system, you might remember that there are these different connections, and they are related by switching a sign on the torsion part of the connection. And there is a similar story going on here, but I didn't write down the details for this either.
Okay, I see. Thank you.
Right. Thanks for the questions. But so the idea is that there are conditions then coming from supersymmetry. They translate to conditions on the geometry, and they translate to conditions on the vector bundles as well. So we have a condition on the gauge vector bundle that it should be a G2 instanton. And I will assume the same condition for theta, the connection on the tangent bundle, because this is when I do that, as I will say in a couple of slides, when I do that, then any solutions that I can find to the supersymmetry constraints will also be a solution to the equations of motion for the heterotic string, provided that this anomaly cancellation condition is satisfied. So this is not true in general, but it has been proven to be true under the assumption that theta is a G2 instanton, that it satisfies this condition here, that the curvature of the connection wedged with psi is equal to 0. Okay, so this is then the definition of the heterotic G2 system. We have these objects, and the geometry satisfies this condition in blue, and the bundle satisfies this condition here in blue. So we have conformally co-closed G2 structures, and we have G2 instanton bundles. Okay, so the first goal then that we will try to get to is to find the moduli of this heterotic D2 system. So and when I talk about moduli, I will only talk about infinitesimal moduli. So this is really a deformation study. So the key idea for an analysis is that we will reformulate this geometry that we have, so this heterotic D2 system, as a nilpotent differential, acting on forms that take value in this in bundle Q, which locally can be decomposed into the tangent bundle, and then the endomorphism bundle over the tangent bundle, and the endomorphism bundle of V. So once I've done that, then I will be able to show that the infinitesimal moduli are counted by a Q-valid canonical D2 cohomology. Okay, so let's do this. So first of all, I want to say something about so I want to define this mathematical structure. So I want to understand what this constraint means, or what this constraint on the D2 structure gives me. So we said that supersymmetry enforced this conformally co-closed condition on the D2 structure, which means that one of the torsion classes is vanishing. Now, exactly in that case, one can define a differential operator, which is defined from the de Rham differential operator, composed with projections to D2 irreps. And so one can define this. So this acts on the way it's written here. So D check 0 here acts on 0 forms and gives us a 1 form. It's just a standard D. Then when this operator acts on 1 forms, then it gives us a 2 form in the 7 irrep of D2. And when it acts on 2 forms, then it gives us a 3 form in the singlet. So this is analogous to how the Dolbeault differential is defined for complex manifolds. And in particular, what is very nice to see is that when this torsion class tau2 is vanishing, then this differential operator defined in this way becomes nilpotent. So this is similar to how the Dolbeault differential becomes nilpotent when you have an integrable complex structure. And for that reason, D2 structures with these constraints are sometimes referred to as integrable D2 structures. Now, integrable D2 structures are also used for D2 structures that are both closed and co-closed. So this might be a bit of a confusing notation. But the reason for it is this connection here between the vanishing of this torsion class and the nilpotency of this operator. So what this means, so one can quite easily see that this operator here is elliptic. And when it's nilpotent, we can then write down an elliptic differential complex, as is done here. And we can use that to define cohomology classes. And these are this cohomology is known as the canonical G2 cohomology. And this was worked out by Reyes-Carrion and Fernandez Ugarte in the 90s. Okay, so we have this. This is a geometric structure that we have. Moreover, we can encode these constraints, the supersymmetry constraints that we have on a bundle, in a similar way. So this constraint that the curvature of the connection should wedge to 0 with psi. This can also be shown that these, together with the vanishing of Tor2, this is equivalent to the nilpotency of a gauge connection or differential dA check, which is defined very much in the same way. So as d check on the previous slides. So we just add these gauge connection terms to the exterior differential, and then we project in the same way to irrep sub d2. So these two supersymmetry conditions can be reformulated as the nilpotency of this differential operator. And then we are left with some more conditions. We have the Bianchi identity, which is the differential of the anomaly cancellation condition. So this must hold for this to be a good heterotic solution. And then we have the equations of motions, as I just mentioned. But from these theorems by Hull, Ivanov, and Martelli-Sparks, we know that if we now assume that theta is a d2 instanton, as we did, then we don't have to worry about the equations of motions. However, we should encode the Bianchi identity into our geometry in some form. So far I've managed to write down some differential operator whose nilpotency condition corresponds to some of the supersymmetry constraints, and the Bianchi identity is left out. So this is the thing that we want to get next. So this was what Sanya, Eric, and I worked out some time ago. So one can show that the supersymmetric n equals to 1 heterotic T2 system that I've just defined is equivalent to the nilpotency of a differential operator, which I will call curly D check. So this operator is defined in this way here. So we have the two differentials, d theta and dA, from the two bundles. Then we have a new connection here, zeta, which is related to the unique, the connection with the unique and symmetric torsion by taking a minus sign here. And then this operator here, it acts on forms that take values in the tangent bundle and these endomorphism bundles. And then there are two maps here, R and F, which I haven't written out here on the slide, but they are defined from contractions with the curvatures of the theta and the A connection on these two bundles. Okay, so we start with this, and then we want to show that the nilpotency condition on this operator here corresponds to the constraints that we have, so that it vanishes if and only, so that d check squared vanishes if and only if the supersymmetry conditions and the Bianchi identities hold. And this is something that we do in a rather pedestrian way. So we compute this, we write it out, and we compute all of these things, and we match the expression that we get to the equations that we started with. Now, and when we do this, then this parameter alpha prime plays a particular role. So alpha prime from a physics perspective is showing us that the terms that are being multiplied by alpha prime, they come from the first correction in a perturbative expansion in this parameter alpha prime. And in principle, there are more such corrections that can be included as corrections to the supergravity theory that we're studying. And we are relying on this kind of perturbative view on the theory when we are proving that the equivalence between these, the vanishing of this, the square of this operator, and the supersymmetry equations and the Bianchi identity. Okay, so we can, what I told you is that we can translate this heterotic D2 system to a constraint on this differential. And the idea then is to use this differential to construct an elliptic complex and identify our infinitesimal moduli of the system with the cohomology that this complex defines. So, so this is what we do then. So we define this complex. One might be a bit worried here that about the ellipticity of this complex, or it may not be obvious why this is elliptic. But this is based on the fact that we started from the canonical D2 complex. So we construct everything very much based on this canonical D2 complex, just allowing the forms that this operator is acting on to take values in different bundles, really. And one can trace everything back and show that since the canonical D2 complex is elliptic, then so is the operator that is defining this complex here. So we find this elliptic differential complex, and we then go on to study the infinitesimal moduli.
And can I just ask, the claim is it's like strictly elliptic. There's not like a gauge problem. It's not like elliptic up to some gauge equivalence or something.
Good question.
Or
I don't think so. But of course, there is a lot of gauge symmetry in this theory. I mean, we have the gauge symmetry of the connection A, and we have the gauge symmetry of the B field. But it doesn't, as far as I can recall, it does not enter into the proof of ellipticity.
I see.
Okay. But it is a good remark. Okay, I will then continue. So in order to study the infinitesimal moduli of this heterotic D2 systems, preserving n equals to 1 supersymmetry, what we did was to consider a family then of such objects, so of such systems that reduces to a heterotic D2 system, so that solves all the constraints when t equals to 0. So we're looking at this, we're doing a deformation study. So we're looking at a small perturbation around the solution that we have, and we keep the linear terms imposing supersymmetry and Bianchi identities, and then the Bianchi identity, and then we read off the constraints that we have on the infinitesimal variations of these different fields. So what kind of variations do we have? Well, we have the variations of the D2 structure, so of the defining 3 form or the 4 form. So these are the geometric moduli, and if we do not have any flux, then it is known that these are counted by the third Durand cohomology on this manifold, so H3. Then we have the variations of the 2 connections. So these are the vector bundle moduli and the variations of the connection on the tangent bundle. So the variations of the vector bundle moduli are given by H1 of NV valued forms, also when H is equal to 0. The variations of the connection on Ty is a bit more subtle, and I'll come back to that. And then we have in H here, H was defined from the exterior derivative of the B field, and Chern-Simons terms coming from these 2 connections. So the degree of freedom that we should vary there is the B field. So this is something that we should include. So 2 remarks, since the if we look at this from a sigma model perspective, where we have the metric B field and dilaton plus the gauge fields, then we see that there's not a complete match here between these different objects. So first of all, since we expect a slight overcount of the geometric moduli, perhaps, since we can change phi without changing the metric. So that's something that we should bear in mind. Moreover, this connection theta here on the tangent bundle it has been argued that this is not really a physical field. This has been discussed in particular in the setting of the Strominger-Hull system by Eric and collaborators in recent years. So I will not say anything more about this, but I just wanted to highlight these two things as being basically considerations that one can make, but that we are leaving for future studies. Okay. So what we did then was to look at these different deformations and see how we would describe them, and if we can count these deformations, or the infinitesimal moduli that correspond to these deformations, in some sensible way. So we started by looking at the geometry. So we have deformations of the G2 structure, so of this 3 form, or of the 4 form. So we can describe that, encode those deformations in a very standard way, which is that we are encoding them in some 1 forms that take values in the tangent bundle. So this is just, so we know that when we vary the 4 form, we should get the 4 form. Any 4 form can be written in this way. So this is a neat way of writing the deformations. And then we can look at, study this matrix MT here to see what it gives. So first we have some constraints on the geometry that we want to preserve. So we had the constraint that Tor2 should be 0. So one can show that this corresponds to this particular condition, that the contraction of d check zeta m, so d zeta was the operator that we had in our the operator d that I showed a few slides ago. So this has to contract to 0, contract with psi and give 0 in order to preserve this condition. So this is the constraint that we have on M then for this to be to preserve the supersymmetry, so to be a modulus of this supersymmetric solution. There are trivial deformations of M. The trivial deformations of the geometry that corresponds to diffeomorphisms. And those can be written in the following form. So we again have this contraction with d zeta of V here, where V is a zero form, which means that our space of geometric deformations can then be written parameterized in the following form, that we have these 1 forms, tangent bundle valued 1 forms that must satisfy this differential condition. And then we should quotient out by the ones that are d zeta check exact. So this d zeta here, this operator can be shown not to be an instanton. It's not a G2 instanton. And this implies that it's not nilpotent. So if we look at this in a general case, then this will not give a finite dimensional space. There can be infinite. If we want to count these kind of deformations, then we can get an infinite number of them. The exception to that is if we have G2 holonomy, because then one can show that there is an isomorphism between this space here and the third de Rham cohomology. But if we do not have G2 holonomy, then this is not enough to get an elliptic complex, and it will not give us the cohomology that we're after. So then we include the other components that go into this heterotic construction. And this is, it's not so strange that we have to do this, because we've seen through these conditions that define the heterotic G2 system that there are relations between the bundles and the geometry through the G2 instanton condition. So we have the condition that F wedge psi should be 0. So here's geometry and here is bundles. So we would expect these to couple in some way. And then we have also through the Bianchi identity or the anomaly cancellation condition, a connection between the B field and the bundles and the geometry. So also there we see that there is a something that should, it's natural to expect that there should be some links between these different components. Okay, so we go on and we look at the bundle, and we find that we have two types of deformations. We have the vector bundle moduli. They are included without any modification. But what we see is that because of this constraint that we get, then the geometric moduli that survive as, or the geometric deformations that survive as moduli, they must lie in the kernel of this map here for this to be true. So for this condition to be preserved. So this means that our moduli space then is not the full space of deformations that I had on the last slide, but it's the kernel of this particular map from this space. This is also not enough to prove finiteness when we have non-zero flux. We need to go on to look at the Bianchi identity as well, to bring in age in the game and also this other bundle. And if we do that, then, and we use this operator that I defined before, then one can show that the constraints, so here are now our variations, they're called ZT, they include the geometry and the bundles, and like so. And we can show that the heterotic constraints that we have, that should be satisfied on the variations, they translate to these fields being D-check closed under the assumption that the B field variations satisfy this constraint. So if we impose this constraint, then we have an implication that these constraints here from heterotic supersymmetry corresponds to this D-check closed condition on these bundle valued fields. And moreover, we can show without any assumption that the diffeomorphism and gauge symmetry, they correspond to D-check exact variations. So then we're done. We have shown that the variations that we have, at least under this condition where we link the geometry deformations to the B field deformations in this particular way, they give us this elliptic complex with the associated cohomology, which counts our moduli. So what have we done then? Well, we have reformulated the heterotic D2 system as an nilpotent differential, which acts on Q-valued forms. And then we have shown that the infinitesimal moduli, they correspond to Q-valid canonical D2 cohomology, H1 D-check here. And since we did this, there have been other studies, for example, from a sigma model point of view, and they our conclusion here agrees that. But what I like to highlight now, and what is something that we've been revising over the more recently, is this assumption that links the B field deformations to the geometric deformations. So what we have realized now in more recent time, like the last year, is that we can indeed relax this condition. It's not necessary, but we can only do so if we enlarge our space of deformations a bit. And in order to do that, I will take a detour over a superpotential. But I've already talked for a very long time, so let me check if you're still with me. Are there any questions?
Yeah.
Okay, I'll just go on. Do I have some time constraints, maybe?
No, we tend to go on past an hour. I mean, maybe
not
maybe
too much.
another
past an
half hour, maybe most.
Okay,
or,
yeah, that should be more than enough.
Okay.
Okay, thanks.
So
I will
actually, sorry, maybe I will
Yeah.
just ask one question just to sort of about this like first half. So in a sense, it's like the whole system is encoded in a sense as like a G2 instanton on this
Yes,
bundle, this big bundle that you create in a sense. Okay, yeah.
That's exactly what we find. So the and I think that's a very nice way of viewing these constraints as well, that the supersymmetry constraints that you have in your physical theory, that those can really be reformulated as the same constraints, but on a bigger bundle.
Yeah, certainly.
Okay, so the superpotential then. I've talked about the moduli space, and I've done a deformation study to say something about the local moduli space close to a solution. And what we find is, of course, only just the infinitesimal moduli there. It's like the tangent space to the moduli space at that point. So we can take an alternative perspective on this and view the moduli space as a critical locus in some off-shell parameter space, where this off-shell parameter space is just any kind of variations that these fields can take. And then the moduli space is some sort of slice or locus where these supersymmetry constraints are being preserved. So in order to encode that, one can define a superpotential, which will define this locus for us. So the strategy here is that we will use physics to do a dimensional reduction from the 10-dimensional heterotic string to 3D, which will allow us to define what the superpotential is for this 3-dimensional theory. And then we will check that the superpotential, and so the vanishing of the superpotential and the vanishing of the variations of the superpotential gives us the supersymmetry constraints for the heterotic G2 system, so that we encode now our n=1 heterotic G2 system in the vanishing of the superpotential and its variation. And then the equations of moduli that we have just derived, they will correspond to the vanishing of the second order variation of the superpotential. There is an equality sign missing here and a 0. And now there's a caveat to this. So 3-dimensional supergravity theories are not as well protected as their 4-dimensional counterparts. So in 4 dimensions, we have strong non-normalization theorems that protect the superpotential from corrections of various sorts. This does not exist in 3 dimensions. So what I'll tell you is what we know about the classical superpotential, but there could also be corrections from other objects, and in particular, one can imagine non-perturbative objects to have to correct this, and also perturbative corrections. I will not talk about that, but this is a caveat. Okay, so how do we do this? Well, we start with the 10-dimensional theory. The 10-dimensional theory is defined by a Lagrangian. The Lagrangian has a bosonic and a fermionic piece. The fermionic piece contains certain terms that will give us when we do a dimensional reduction, will contribute to the mass term for the gravitino in 3D. Now the mass term for the gravitino has to vanish for supersymmetry to be preserved. So this is the term that will define our superpotential. So we compute this by dimensional reduction, and the result is that we get an expression which looks like this. So this is our superpotential. It contains the G2, the forms that define the G2 structure, so phi and psi, their exterior derivatives. So we have the torsion here. We have H, the three-form flux, and we have the dilaton phi here. And then we have a term little h here, which is the a term that will set the three-dimensional cosmological constant, which can either be 0 or negative. So we can either get Minkowski or ADS solution from this. Okay, so this is our expression for the superpotential. We have found it by standard methods. So now we want to show that on the locus where this is vanishing, then the n equals to 1 conditions hold for the heterotic D2 system. So then we need to think about what the parameter space is, this off-shell parameter space. And what we have then is the variation of the dilaton and the geometry encoded in this one form M, and then the variations of the bundles and the B field. So what we do then is that we take our superpotential, we vary it with respect to these fields, and then we get this expression here just by direct computation. And what we can see then is that we can recognize some of the constraints that we've seen before. So here we have the condition that phi is covariantly co-closed. Here we have the D2 instanton conditions for the bundles. So these are our supersymmetry constraints. Then these terms which are orange here, they do not look as nice, but they include H, so the flux, and the torsion here through this d phi, and also the dilaton. And one can massage these to show that they are equivalent to equating H with T, torsion, this little h with one particular component of the torsion, and setting the superpotential to 0. So here we have the superpotential up here. So these are the constraints. So we see that if we the critical points then of the superpotential, they do correspond to the heterotic D2 system with these constraints, and this is really a constraint of the heterotic D2 system. Now we have this new parameter here, which is the cosmological constant in 3D, which is also included here. Okay, so this works. The first order variations of the superpotential reproduce the supersymmetry conditions. So then we want to go to the second order variations, and we want to reproduce, we want to see that the superpotential reproduces this elliptic differential complex and the counting of this infinitesimal moduli, and where the infinitesimal moduli were these Q bundle valued forms that were closed, and so D-check closed, but not D-check exact. So in order to reproduce this, then the superpotential should have a form that looks something like this. So the bracket here, it's basically just wedge and contract indices, these Q bundle valued indices. We have the dilaton here, and we have the 4 form here. So this is 1 form, this gives us a 2 form, and then 4 forms, so we get 7 forms. So that's looks nice, at least. So this is what we expected, and this was where we started about a year ago, trying to write this down. But then we ran into some problems which was related to this constraint, this condition that we had on the way that we had related the variations of the B field and the geometry. So really what's happening here is that when we think about this from this off-shell parameter space point of view, then the variation of the dilaton and the B field is something that we want to keep as free as possible until we impose the supersymmetry conditions. And it's not necessary that, so when we wrote this thing down, then we kept the dilaton fixed, and we had this constraint that a particular combination of geometric deformations and B-field deformations should be closed. So writing the superpotential in this, or finding an expression for the superpotential which only contains these fields here, the Z's, is perhaps asking a bit too much, or at least we couldn't get it to work, because we're really leaving out some degrees of freedom. So taking that at face value, we then looked at what are the constraints that we get if we then let the dilaton and this, so I've decided to collect this particular combination of geometric deformations and B-field deformations into a field which I call beta. And then I have my variations, or the field space that I'm interested in, parameter space, are then given by these three terms, where we have variations of dilaton, variations of geometry and bundles, and some variations of the B field in here, the ones that we had before here, and then beta are the ones here. So let's look at this and see what kind of structure we can find. So first of all, we can check that indeed, if we take this approach and we vary the superpotential with respect to all of these fields, then we do reproduce all of the equations for the moduli of the heterotic D2 system. They look like this. So this is going a bit beyond than the deformation study that we did in 2017. And moreover, we can define a new complex which encodes all of these degrees of freedom, but which is now, a bit on top. So actually, maybe let me just show it. So here is the bit, more or less the bit that we had before. So the bit with Q-valued forms and the operator D. So this is the bit which gave us the D-check cohomologies that I talked about before. We've decided to, rather than writing out the projections, we are here wedging with the closed four form, so e to the minus 2 phi psi. It gives us the same thing, just a bit easier to work with. So this is the bit that we had before, and now we're extended that with one complex here, which is related to the deformations of the dilaton, and one complex here, which is related to the deformations of this field beta, so this particular combination of geometric and B field deformations. So we can write down this graded complex, and what is it? Well, it's a graded complex for a vector space, which corresponds to certain certain spaces of differential forms. It has a differential D, which is nilpotent and self-adjoint with respect to a symplectic pairing. We can write the superpotential in terms of this symplectic pairing in this way here, and this will give us an elliptic complex which has this stratification. So it's a combination of three complexes, and the physical, or the parameter space that we're interested in, so the deformation space, that's captured by the fields in zero homological degree. So they sit here. So here we have beta, we have the Q-valued 1 forms, that was the geometric deformations and the bundle connection deformations. And then we have the dilaton deformation, which goes very nicely together with this four form psi, since we get something that is closed from e to the minus 2 phi psi. So this is why this is a full form here. So these are our physical fields, and then we can encode other aspects of our three-dimensional theory. So we have gauge symmetries of the B field and of the geometry, which is encoded here. And then we have a gauge symmetry for the B field. So the B field is a two form. So it has a gauge symmetry, which is a one form. And then we have gauge of gauge symmetry for that one form. So this gives us these components in this lower complex here. Then we have the gauge symmetries of the diffeomorphisms of the geometry and the gauge symmetry of the bundles given here. And then we complete this in order to get an elliptic complex which has this shifted symplectic structure given by a symplectic form. So there are self-duality constraints on these maps here, which are very similar to the maps F and R that I showed some at the very beginning of this talk. So to be more concrete, we can write this differential operator as a matrix in this form here. So here we have the differential operator that we found some years ago. And then we are complementing that with just the Rham differentials with these projections, and then these maps T and S here, which are determined by the constraint that this complex should match the superpotential that we have found and its second order variations, and correspondingly the equations of moduli. So this is what we have. So once we have set this up, and once we have defined these order by order in homological degree, then we can check whether this works, whether this gives us an elliptic complex, and it does. So nilpotency, for example, is something that follows once we have defined everything in order to match the equations for the moduli and the gauge symmetries of this 3D theory. Okay, so this is what we find. So then we can return to the question of the infinitesimal moduli then, and just remove this constraint that we had, keeping the dilaton fixed and keeping beta closed. So if we relax that, then we see that the infinitesimal moduli are now captured by this kind of cohomology. So from the complex that I just showed here, we can write down what this is. So we have our fields here, the parameters that we're interested in. They are living here, and the non-trivial ones are the ones which are D closed, but not D exact, where with the D I mean this particular operator here. I'm running out of Ds. Okay, so this is where we are, and we're now working a bit towards understanding the quantum aspects of this theory. So the idea here is that we want to compute the one-loop partition function. For doing that, we only need the quadratic action, so we can define then as our action the second order variations of the superpotential, and use that to compute our one-loop partition function. But since we have so much gauge symmetry in our theory, we need to fix this gauge. So we can do that using the Bartolin-Minkowski formalism, which requires us to specify a gauge fixing Lagrangians. And this is something that we're currently exploring, and I hope to have something to say in some time. But I did hope to have something to say already a year ago on this, because we had started thinking about it then. There are some subtleties that are very hard to work out, but we think we'll get there. So with that, let me conclude. I've told you about the heterotic D2 system and the geometry and moduli of that system. And the key idea here is that we've been exploring is to translate the supersymmetry constraints into geometrical constraints and writing down elliptic complexes that define both our heterotic D2 system and also the moduli of these systems. And as a tool to getting to that, the superpotential for this three-dimensional theory seems to be very good to use. So the outlook then is that while we're working on this this quantization of this system, and the reason why we're doing that is because there have been works and people have worked on similar problems in the past. So in particular, there are some papers on what is known as the topological D2 string by De Boer and collaborators, where they are exploring this kind of G2 instanton bundles and how they relate to what one can say about their one-loop partition function. So we hope to connect to that. Also, Eric has been working with other people on exploring this kind of problem in the Strominger-Hans system, and has a very nice paper on the heterotic Cordera-Spencer theory that came out last year. So we hope to connect also to that kind of discussion. And then beyond that, there are different things that one can look at. So we have yet to compute these cohomologies in explicit examples. It hasn't really been done. One can certainly continue. So we've now studied this system at linear order, and with the superpotential, we're going to quadratic order, but one can go higher and try to both look at higher order deformations and maybe also looking at finite deformations. And then anything that we could say about the geometry of moduli space, what the metric is, and so on would be very interesting. So with that, let me thank you for listening.
Yeah, thank you. Are there questions? Well, go ahead, Friedrich.
How hard would you think that the higher order deformation? I mean, I expect that's super complicated to calculate the higher order deformations, right?
Yeah.
Okay.
So we have some loose speculations about some that I mean the theory has structure, so maybe it's not we don't expect it to be completely impossible to study higher order deformations, but it's certainly getting more and more complicated for each step that we take.
Right.
So I would not, yeah, maybe there is some insight that we're still lacking for it to be completely tractable, but yeah, difficult, but maybe not impossible.
I see, thanks.
I wonder, could you go back to this slide with the superpotential?
This one? Oh, sorry.
Yeah, okay. Yeah, so little h is this tau naught, which is part of the torsion. So somehow it is, oh, I see. Yeah, it's you have like a quadratic term in the torsion and also a term involving the derivative of the torsion. Because you have this d phi.
There's no, so d phi just gives torsion, right?
Oh, sorry. Yes. Oh.
So there's no quadratic term.
Oh, yeah. I guess I somehow imagined that this was somehow like sorry, my use of the physics terminology is so bad, but like this like string effective action in disguise or something. Is that not right?
I'm not sure I understand what you
Yeah, I'm
mean.
probably not using the right words, but like for me, all of my understanding of these string equations kind of starts with this action, this kind of modified Einstein-Hilbert action, which is like scalar curvature minus 1/12 h
Oh,
squared
yeah.
measured against a dilaton.
Exactly, yeah. So so that would be the 10-dimensional action that you start with. Right, and what you're talking about is the bosonic sector of that, which is normally all you're looking at, because that's the thing that sets your that gives you your equations of motion and so for the bosonic fields. Now, in order to find the superpotential, since the superpotential is given by the gravitino mass, and the gravitino is a fermion, we need to look at the fermionic part of the 10D action. And that is what goes into this dimensional reduction to the superpotential. So maybe that
I see.
there's something that these terms come from a different place than.
But somehow this is a functional characterizing. I mean, the critical points of this thing are
yes, but that because then we it is, yes, but the really the logic in how it emerges is from these terms here, which are part of the 10-dimensional action, but that you normally don't look at so much.
I see.
Because you're focusing on the bosonic sector. So it's but once you have so this is the trick then to sort of to get the superpotential, because the superpotential is related to the gravitino mass. You're looking at the fermionic sector to write down what it is, but then once you have it, then it contains your bosonic fields again. So it's of course, I mean, I do have some extra slides with some more details on this, but I'm not sure if it would be.
Well, maybe let me just ask a related question. So you mentioned this like bosonic sector, which gives you the equations of motion. Are these equations that you describe are they some kind of special dimensional reduction of those classic equations of motion? Is that known or thought to be true? Or
well, supersymmetry. So what we want is to write down something that gives us the supersymmetry equations, not the equations of motion. So the equations of motion for the theory, those I can derive just from the bosonic action. So if basically what you do is you set all your fermions to be 0. And then you forget about them, then you look at the bosonic part. And then you say that, okay, can I do this? Well, yes, it will still be supersymmetric, provided that the variations of the fermions are all vanishing, because that gives you the supersymmetry conditions. But always when you have supersymmetry, you need to look at both the fermions and the bosons, and you need the full theory to know what the supersymmetry constraints is. And what the superpotential is, it's basically reflecting that in order to derive the supersymmetry conditions, you need to have information about the fermions and the bosons in the theory. I'm not sure I'm doing it very well.
But I always had the impression too that like these sort of supersymmetric constraints are stronger than the equations of motion. The equations of motion are somehow much more general or something. Is that not correct in this?
Yes and no. So you can have, so if you have a supersymmetric solution to the supersymmetry constraints, then that will typically solve also some of the equations of motion. Not necessarily all, but at least some. So by solving the supersymmetry constraints, you're typically gaining something on your equations of motion. And in this particular setting of flux compactifications, there are these nice theorems saying that, okay, if you solve the supersymmetry conditions plus the Bianchi identity for the H flux plus making this assumption on this connection theta, then you have your equations of motion. And in other situations, you will have similar kinds of theorems.
And so is that the case here? Do you have some kind of equation of motion underneath?
Yeah, so I'm sure, but the equations of motion, of course, they are quadratic equations, and the supersymmetry conditions are linear equations, or first order differential equations.
Yeah.
So they are different. It's not like I can write so proving that the supersymmetry conditions imply the equations of motion is something that takes some work to do.
Sure.
And it's not obvious from the get-go how this works. But the other thing is, how do we actually derive the supersymmetry conditions? So the supersymmetry conditions that we want to reproduce with the superpotential. Well, the way that those are derived is by looking at the action with both fermions and bosons, and then checking what kind of transformations of these fields that would send fermions to bosons and bosons to fermions that would preserve the action. That is the supersymmetry that we're after. So then there will be constraints on the fields coming from that study of the action with all of the degrees of freedom, and those supersymmetry conditions, they are then the ones that we are the linear or the first order differential equations that we're looking at. So
Okay.
that's that's what we get. So that is why, in order, if we want to write down the superpotential that encode those conditions, then that superpotential better know something both about fermions and bosons. And in particular,
I see.
Since when we say supersymmetry constraints, we typically talk about the supersymmetry constraints for that we want the supersymmetry variations of the fermions to be 0. Then we should have a superpotential which we derive starting from the fermionic sector of the theory.
Okay, yeah, thank you. Any more? Okay, yeah, so let's thank Magdalena again.
Thank you.